Okay, so in order to find the solution of a system of linear equations using determinants, we have to make sure that we are working with matrices that are invertible, so matrices that have a inverse. So the following criterion allows us to determine whether a square matrix has an inverse or not. So remember last time we went over how to find inverses and how to calculate them. So we can actually use determinants to see if a matrix has an inverse, because if a matrix, a square matrix A, is invertible, then its determinant cannot be equal to 0. So if you can calculate a determinant and it's 0, then that matrix is not going to have an inverse. Okay? So remember that only square matrices are matrices. So if the matrix is not square, then it's not invertible. And then if the determinant of that matrix equals 0, then it's not invertible. All right, so let's see how to use determinants to solve systems of linear equations. So if we have a n linear system equations with n unknowns, so my n knowns are x1, x2, xn, and the coefficient matrix D is not 0, then we can use what we call Cramer's rule to solve the system. So first let's look at the setup. So I have a system of n equations with n unknowns, x1, x2, xn, okay, and these are the constant terms. So if I have this system, the coefficient matrix, which we want to call D in this case, remember from last time, what is the coefficient matrix? You just put the coefficients in order. So A11, A12, A1n, A21, A22, A2n, and then the last row AN1, AN2, ANN. So this is the coefficient matrix D. So if the coefficient matrix D is not 0, then we can use Cramer's rule to solve the system. Also, this matrix has to be invertible, so the determinant cannot be equal to 0. So what does this Cramer rule says? Let's think about it. So let's write this system of linear equations in matrix equation. So in matrix equation, this is going to be D times x1, x2, xn equals b1, b2, bn. So I can write this as D times x equals b. So where D is the coefficient matrix, x is your unknown matrix, and then b is your constant term matrix. So if you are in this setup and you want to solve this, so you want to solve x1, x2, and xn, the Cramer's rule, you have to make sure that the determinant is not 0. So if the determinant of the coefficient matrix is not equal to 0, then Cramer's rule says that x1 is going to be this determinant, so the determinant x1, I'll tell you in a little bit what that is, divided by the determinant of D. x2 is going to be the determinant of x2 divided by the determinant of D, and so on. So let's see what are dx1 and dx2 and so on. So the determinant of dx1, this is going to be the determinant of the coefficient matrix, but instead of row 1, because instead of column 1, we're going to put the constant terms. So the determinant corresponding to x1 is going to have b's on the first column, and the rest stay the same. So it's going to have b1, b2, bn, and then the other coefficients stay the same. So a12, a1n, a22, a2n, and then a2n2, ann. So dx1 is the same as the coefficient matrix, but instead of column 1, you're going to have the constant terms. So what's going to be dx2? The determinant of dx2 is going to be the same as the coefficient matrix, but instead of column 2, you're going to have the b's. So the first column stays the same, but column 2 becomes b1, b2, and bn. And then the rest stays the same. And then the x3, the x4, and so on will be the same thing. So notice that solving the system, aka finding x1, x2, and xn, is going to come down to calculating determinants. So that's why we're saying that we're solving systems of linear equations using determinants, because solving them comes down to calculating determinants, and we know how to calculate determinants now. So let's see an example. So we are to solve this system of equations using Cramer's rule. This should be equations. So first of all, Cramer's rule says that if the determinant of the coefficient matrix is not 0, then we can find x1, x2, and so on by calculating this determinant. So first we have to find the coefficient matrix D. So the coefficient matrix D is just going to be the coefficient of x, y, and z. So in my case, x1, x2, and x3 are called x, y, and z. So it's going to be 2 for x, -3 for y, and 4 for z. 1 for x, there's no y in here, so it's 0, and then 6 for z. 3 for x, -2 for y, and there's no z here, so it's 0. So plus 0z plus 0y. Okay, so in order to use Cramer's rule, make sure, check that the determinant of D is not equal to 0. Because we're dividing by the determinant of D, which is just a number, so we cannot divide by 0. So we can't apply Cramer's rule to find x1, x2, and xn if we're dividing by 0. So let's find the determinant quick. So determinant of D is going to be determinant 2, 1, 3, -3, 0, -2, 4, 6, and 0. So what's a good row to expand by? Should we expand by row 1 or row 2 or row 3? Well, row 2 and row 3 have a 0 in it, so it's going to be simpler because it's going to come down to calculating 2 minors instead of, if we do it by row 1, we're going to have to calculate all 3 minors. So let's do it by row 2. Okay, so we're going to take the first entry, 1, and then times -1 to the, what's the index in here? It's row 2, column 1, so 2 plus 1. And then the minor, if I remove row 2, column 1, the minor that I have left is -3, 4, -2, 0. Plus, the second element is 0, so I don't even need to do the work. I'll just put plus 0. And then the third element is 6, so it's going to be plus 6 times -1. 6 is in row 2 and column 3, so -1 to the 2 plus 3. If I remove the column corresponding to 6 and the row corresponding to 6, then it's 2, -3, 3, -2. There you go. So then the determinant of D is going to be equal to -1 to the 2 plus 1 is negative. So it's going to be minus -3 times 0 is 0, minus 4 times -2, so minus 8. -1 to the 5th is negative, so it's going to be minus 6 times the determinant of this is -4 minus -9. So I'm going to get -8 is positive 8, with the minus is -8, minus 6 times -4 plus 9, that's 5. So it's going to be -8 minus 30, so the determinant is -38. -38 is not equal to 0, so we checked that. So we can use Cramer's rule. To solve for x, y, and z. So according to Kramer's rule, what is my x going to be equal to? My x is going to be equal to the determinant of x, so removing the column corresponding to x and replacing it with the constant terms. So let's just write down. So x is going to be equal to the determinant of d, where I remove the column for x, and I'm going to replace it with the constant term. So the constant term, our b, is right here, 105, and then divided by the determinant of d. So let's find that. So I found that the determinant of d is negative 38, so this is going to be divided by negative 38. Let's write the determinant corresponding to x. So it's going to be in d, instead of the first column, I'm going to write the b's. So it's going to be 105 and then negative 302 and then 460. So 105 instead of the x, and then the rest stays the same. Okay, now we got to calculate this 3 by 3 determinant. So look at it and think about what would be the best row to expand by. What's the row that has the most zeros? Well, row 2. Row 2 has only one entry, so it's going to be 0 times the cofactor for 0, but 0 times anything is going to be 0, plus the second term, which is also 0, times the cofactor of that, but 0 times anything is 0. So the only one we're going to calculate is 6 times negative 1. 6 is in row 2 in column 3. Times its minor. So its minor is going to be, if I remove row 2 in column 3, I get 1, negative 3, 5, negative 2. Over negative 38. So then x is going to be equal to negative 1, so negative 6 times this determinant, 1 times negative 2, minus negative 15, divided by negative 38. So this is going to be negative 6, negative 2 plus 15. So this is going to be negative 6 plus times 13 over negative 38. So it's just going to be 30. Let's reduce by 2. This is 19 and this is a 3. So negative 3 times 13, that's 39 over 19. So this is the value for x. We solved for x. Now let's solve for y. So y is going to be the determinant when we remove the column for y and replace it with the constant term over the determinant of d. So let's see. So the determinant of d is negative 38. Let's write down what is the determinant when we remove y. So the first and third column stay the same. And then I replace the second column by the b's, constant terms, 105. Okay, so then we're going to have to find the determinant of this 3 by 3, and we can expand by either row 2 or row 3 because they have a 0 in it, or column 2 and column 3. So let's do it by row 2. So it's going to be 1 from here times negative 1 to the, this is in row 2, column 1, so 2 plus 1, times its minor. So when I remove row 2, column 1, I get 1, 4, 5, 0. Plus the second element is 0, so it's just going to be plus 0. Plus the third element is 6 times negative 1 to the row 2, column 3, so 2 plus 3, and the minor. So the minor will be, I'm removing row 2, column 3, so it's going to be 2, 1, 3, 5. 2, 1, 3, 5. and then divided by negative 38. So y equals, it's probably a good idea to calculate these determinants separately rather than have all this work here. So it's going to be negative 1 times 1 times 0, 0 minus 5 times 4, 20, minus 6 times 2 times 5, which is 10, minus 3 over negative 38. So this is going to be 0, negative, so positive 20 minus 6 times 7 over negative 38. So it's going to be minus 42, 20 minus 42 minus 22 over negative 38. That's 11 over 19. So that's y. So finally, let's see what z is. So z is going to be the determinant of the coefficient matrix where we replace column 3 with the constant term column over d. So let's do dz separately. So dz is going to be, the first column stays the same, second column stays the same, right? First column stays the same, second column stays the same, and then the 460 is replaced by 105. Notice that it's nice to expand by row 2 because it has 2 zeros. So it's just going to be 1 times negative 1 to the power row 2 column 1, 2 plus 1, times the determinant left when I remove row 2 and column 1. So 3, 1, negative 3, 1, negative 2, 5. And then plus 0, plus 0. So it's going to be negative 15 from here, and then minus negative 2 times 1, so plus 2. So it's going to be negative 13, so it's going to be positive 13. So that's what I'm going to put instead of this one. So positive 13 divided by, I know that the determinant of d is negative 38. So this will be the answer. So this is it. We solved for x, y, and z using Cramer's rule. So we first had to make sure that the determinant of the coefficient matrix is not 0. And once we calculated that, then we have to go ahead to use Cramer's rule. And Cramer's rule comes down to solving, calculating a bunch of determinants. So this is how we use determinants to solve systems of linear equation. So we have done a lot with systems of linear equations. You have a lot of calculations in this chapter, and obviously on the exam you can use whatever. If you're asked to solve a system of equations, you can use whatever method you want unless it's stated. You know, if they ask you what would be dx, then that means that you have to do it with Cramer's rule. Alright, so that will conclude our study for systems of linear equations using matrices.